At the end of the 19th century, classical physics stood with extraordinary confidence. For more than 200 years, it had explained the motion of planets, the behavior of fluids, the flow of heat, the propagation of sound, and the nature of light with astonishing precision. The universe appeared to operate like a vast, predictable machine governed by continuous laws. Every physical quantity could vary smoothly, and with enough information, the future could be calculated exactly. Many leading scientists openly believed that physics was essentially complete, that only minor refinements remained. This sense of closure created an intellectual atmosphere in which deep contradictions were not expected, and certainly not welcomed. Yet beneath this confidence, subtle cracks were already forming. One of the most troubling areas involved the interaction between matter and radiation. Light had been successfully described as an electromagnetic wave thanks to the work of James Clerk Maxwell, whose equations unified electricity, magnetism, and optics into a single elegant framework. These equations were so successful that they seemed unassailable. Combined with classical thermodynamics and statistical mechanics, physicists believed they possessed all the tools necessary to describe how objects emit and absorb radiation. There was no expectation of fundamental failure, only the challenge of carrying out difficult calculations. The problem emerged when scientists turned their attention to heated objects. Everyday experience shows that as an object warms, it begins to glow. At first it emits dull red light, then orange, yellow, and eventually white as the temperature increases. This progression is not unique to metals or specific materials, it appears universal. To study this behavior precisely, physicists used idealized systems that absorbed all incoming radiation and emitted it purely as a function of temperature. These systems revealed a precise relationship between temperature and the spectrum of emitted light. Experimental measurements were consistent, reproducible, and remarkably accurate. Classical physics attempted to explain this phenomenon using well-established principles. The electromagnetic field inside a heated cavity could be treated as a collection of standing waves. Each wave mode could store energy, and according to classical statistical mechanics, energy should be distributed equally among all available modes. This idea, known as equipartition of energy, had worked successfully for gases and solids. There was no obvious reason it should fail for radiation. The mathematics seemed straightforward, and the assumptions were deeply ingrained in physical thinking. However, when physicists carried out the calculations, the results were shocking. The equations predicted that the energy emitted at shorter wavelengths should grow without bound as wavelength decreased. In practical terms, this meant that a warm object should radiate enormous amounts of energy in the ultraviolet and higher frequency regions of the spectrum. This prediction was not just slightly wrong, it was catastrophically wrong. Experiments showed that emission peaked at a certain wavelength and then dropped sharply at higher frequencies. The classical theory diverged wildly from reality. This discrepancy could not be dismissed as experimental error. Measurements were refined, repeated, and verified across different laboratories and materials. The failure was theoretical, not empirical. Classical physics, which had explained so much, was now producing an infinite result where nature clearly showed a finite one. This was deeply unsettling. Infinity in physics often signals a breakdown in assumptions, and here it appeared in one of the most basic processes imaginable: how matter glows when heated. The situation was particularly disturbing because the failure did not arise at extreme conditions or exotic scales. It appeared in ordinary laboratory experiments involving temperatures and materials that physicists handled every day. If classical theory could not explain something so common, what did that say about its claim to completeness? The ultraviolet catastrophe, as it later came to be called, was not merely a technical problem, but a philosophical crisis. It challenged the belief that the physical world could be fully understood through continuous laws alone. Attempts were made to rescue the classical framework. Some physicists hoped that refinements to electromagnetic theory or modifications to statistical mechanics might resolve the issue. Others speculated that imperfections in experimental setups or material properties could account for the discrepancy. But these efforts consistently failed. Partial formulas could match observations at long wavelengths or low frequencies, but they broke down elsewhere. No classical approach could reproduce the full experimental curve. This failure revealed something profound about the limitations of classical thinking. Classical physics assumed that energy could vary smoothly, and that systems could exchange arbitrarily small amounts of it. It also assumed that the microscopic constituents of matter behaved in ways directly analogous to macroscopic objects. These assumptions had gone largely unquestioned because they worked so well in other contexts. The Blackbody problem exposed the danger of extrapolating successful ideas beyond their domain of validity. Equally important was the psychological impact on the scientific community. The late 19th century was a period of intellectual triumph, and the idea that foundational principles might be wrong was deeply uncomfortable. Many physicists initially viewed the Blackbody problem as an anomaly that would eventually be resolved within existing theory. Few were willing to entertain the possibility that something fundamentally new was required. This resistance slowed progress, but also highlighted how revolutionary the eventual solution would need to be. The failure of classical physics in this context did not mean that its laws were useless or incorrect in general. Newton's laws still described motion accurately, Maxwell's equations still governed electromagnetic waves, and thermodynamics remained valid at macroscopic scales. What the Blackbody problem revealed was that these laws were incomplete. They were approximations that worked within certain limits, but failed when pushed into regimes involving very small scales and high frequencies. In hindsight, this failure appears almost inevitable. Classical physics was built on intuition derived from everyday experience, where continuity and smooth change dominate. The microscopic world does not operate under the same rules, and the Blackbody problem was one of the first clear signs of this mismatch. It showed that nature contains layers of behavior inaccessible to classical reasoning alone, layers that require new concepts and new mathematics. This realization marked the beginning of a transformation in physics. The failure itself was the catalyst. Without the stubborn refusal of Blackbody radiation to conform to classical predictions, there would have been no reason to abandon deeply held assumptions about energy and continuity. The crisis forced physicists to confront the limits of their knowledge and opened the door to a new understanding of reality. The Blackbody problem thus represents more than a technical challenge, it represents a moment of intellectual humility. It reminds us that even the most successful theories can fail, and that progress often begins not with answers, but with contradictions. Classical physics did not collapse overnight, but its inability to explain Blackbody radiation revealed that the foundations of physical theory were incomplete. From this failure emerged the need for a radical new framework, one that would eventually redefine the nature of energy, matter, and light itself. As the implications of the Blackbody problem became impossible to ignore, the failure of classical physics grew more severe and more revealing. What initially appeared to be a narrow mismatch between theory and experiment gradually exposed a structural weakness at the heart of 19th century science. The equations were not merely inaccurate, they were conceptually misaligned with nature itself. This realization unfolded slowly, resisted fiercely, and ultimately transformed the identity of physics as a discipline. One of the most unsettling aspects of the crisis was that the incorrect prediction arose from principles that were otherwise extraordinarily successful. The idea of equipartition of energy, derived from classical statistical mechanics, had explained the behavior of gases with remarkable precision. According to this principle, every independent mode of a system should carry the same average energy when in thermal equilibrium. Applied to the electromagnetic field inside a cavity, this meant that every possible standing wave mode should receive an equal share of energy. Since there are infinitely many modes at higher frequencies, the total energy diverged. The mathematics was internally consistent, logically sound, and disastrously wrong. This was not a careless error. The calculations were carried out by some of the most brilliant minds of the era, including Lord Rayleigh and James Jeans, whose work led to what is now called the Rayleigh-Jeans law. Their formula matched experimental results at long wavelengths perfectly, reinforcing confidence in the approach. But as the wavelength shortened, the prediction spiraled toward infinity. The theory did exactly what classical assumptions demanded, and that was precisely the problem. This moment revealed a painful truth: correctness in one regime does not guarantee universality. Classical physics had been extrapolated far beyond the domain in which it had been tested. The microscopic realm of atoms and radiation was being treated as a scaled-down version of the macroscopic world, governed by the same intuitions of continuity and smooth variation. The Blackbody problem demonstrated that this extrapolation was unjustified. Nature, at small scales, was playing by different rules. What made the situation even more troubling was the absence of any obvious experimental anomaly. The data were clean, stable, and unambiguous. There was no noise to blame, no faulty instruments to recalibrate. The curve of Blackbody radiation emerged again and again with stubborn consistency. Theory, not experiment, was on trial. For a scientific culture that prized mathematical elegance and predictive power, this was a humbling experience. The philosophical consequences were profound. Classical physics rested on determinism and continuity. Every effect had a cause, every variable could change smoothly, and randomness was merely a reflection of ignorance, not a feature of nature. The Blackbody problem threatened this worldview. If classical assumptions led to infinite energy output from ordinary objects, then something fundamental was wrong. Either the mathematical framework was incomplete, or the underlying conception of reality was flawed. Many physicists initially underestimated the depth of the crisis. They believed that a clever adjustment or a missing factor would eventually restore harmony. Some proposed modifications to the interaction between matter and radiation. Others questioned the applicability of equipartition at high frequencies. These efforts produced partial successes, but no complete solution. Each fix repaired one part of the curve while breaking another. The failure was systemic, not local. This resistance to radical change was not irrational. Classical physics had earned its authority through centuries of success. It had unified celestial and terrestrial motion, explained electricity and magnetism, and laid the groundwork for modern engineering. Abandoning its core assumptions felt premature, even reckless. Yet the Blackbody problem forced an uncomfortable confrontation. A theory can be powerful and still be incomplete. The crisis also revealed an important lesson about scientific progress. Breakthroughs do not always arise from bold new ideas, sometimes they emerge from persistent failure. The Blackbody problem did not hint at quantization directly. It simply refused to be explained. Its significance lay in its obstinacy. By resisting all classical solutions, it compelled physicists to question what they had taken for granted. This questioning gradually shifted attitudes within the scientific community. Younger physicists, less invested in the classical worldview, became more open to unconventional ideas. The problem began to be seen not as an embarrassment to be hidden, but as a doorway to deeper understanding. The failure itself became a source of information, a clue pointing toward new principles yet to be discovered. The inability of classical physics to explain Blackbody radiation also highlighted the limits of human intuition. Concepts like continuity and smoothness feel natural because they align with everyday experience. But nature at the microscopic level is under no obligation to conform to human expectations. The Blackbody problem served as an early warning that intuition must sometimes yield to evidence, even when the evidence contradicts deeply held beliefs. In retrospect, the crisis was not a sign that classical physics was wrong, but that it was incomplete. Its laws remained valid within a certain range, much like Newtonian mechanics remains useful despite the existence of relativity. The blackbody problem marked the boundary beyond which classical ideas could no longer be trusted. It identified the edge of applicability, a frontier where new physics was required. This boundary was not marked by dramatic explosions or cosmic extremes, but by something deceptively simple: the glow of a heated object. That simplicity is what makes the failure so striking. It showed that revolutionary insights can arise from ordinary phenomena, provided they are examined with enough precision and honesty. The most profound mysteries are sometimes hidden in plain sight. By exposing the inadequacy of classical assumptions, the blackbody problem prepared the ground for a conceptual revolution. It cleared space for ideas that would have seemed unthinkable only decades earlier. Discrete energy levels, probabilistic behavior, and the breakdown of determinism would soon follow. None of this would have been possible without first acknowledging that the old framework had reached its limits. The failure of classical physics in the blackbody problem thus represents a necessary collapse, not a defeat. It was the moment when physics stopped pretending to be finished and began to reinvent itself. By confronting an infinite prediction that nature refused to obey, scientists were forced to abandon the illusion of completeness. From that humility emerged the foundations of modern physics, built not on certainty, but on a willingness to rethink reality itself. To understand why the blackbody problem became so decisive, it is essential to understand what physicists meant by a blackbody and why this seemingly abstract concept carried such enormous importance. A blackbody is not an everyday object found neatly labeled in nature. It is an idealized system, a conceptual tool created to strip away complications and reveal a fundamental relationship between matter, radiation, and temperature. Precisely because it was idealized, it allowed physicists to ask a very pure question: if all material details are removed, how does energy itself behave? The idea of the blackbody emerged from attempts to understand thermal radiation in a universal way. Ordinary objects emit light and heat, but their radiation depends on surface texture, chemical composition, color, and shape. A polished metal behaves differently from a rough one, and a dark surface radiates differently from a reflective one. These variations made it difficult to identify general laws. Physicists needed a system that would eliminate material dependence entirely, leaving only temperature as the controlling variable. The blackbody was designed to be exactly that system. In practical terms, a blackbody was approximated by a hollow cavity with a small hole in its wall. Radiation entering the hole would bounce around inside, reflecting repeatedly from the interior walls. With each reflection, some energy would be absorbed, and after many reflections, almost none would escape. The hole therefore acted as a nearly perfect absorber. At the same time, when the cavity was heated, radiation escaping through the hole represented the energy distribution inside the cavity. Remarkably, this radiation depended only on the temperature of the cavity, not on the material of its walls. This made the cavity radiation an almost perfect realization of blackbody behavior. This insight was crucial because it revealed a universal phenomenon. The radiation emitted by a blackbody was not tied to copper, iron, carbon, or any specific substance. It was a property of nature itself. This universality made blackbody radiation one of the cleanest experimental windows into the laws governing energy and light. If physics could not explain this, then it could not claim to understand thermal radiation at all. The conceptual foundation for this universality was laid earlier in the 19th century by Gustav Kirchhoff, who demonstrated that the ratio of emissive power to absorptive power is the same for all bodies at a given temperature and wavelength. This meant that a perfect absorber must also be a perfect emitter. Kirchhoff's insight transformed blackbody radiation from a curiosity into a central problem. It suggested that there existed a single, universal radiation function waiting to be discovered, one that classical physics should, in principle, be able to derive. What made the blackbody so important was not just its idealized nature, but its role as a testing ground for theory. Unlike complex systems with many variables, the blackbody reduced the problem to essentials: temperature in, radiation out. If theory could not explain this relationship, then something fundamental was missing. This is why the blackbody problem was so devastating. It was not an edge case or a special material behaving strangely. It was the simplest, cleanest scenario imaginable. The measurements themselves were extraordinarily precise. As experimental techniques improved, physicists were able to map the blackbody spectrum with great accuracy across a wide range of temperatures. The results showed a smooth curve with a clear peak that shifted predictably as temperature changed. This peak moved toward shorter wavelengths at higher temperatures, a behavior that would later be summarized in Wien's displacement law. At lower frequencies, the intensity rose gradually, while at higher frequencies, it dropped sharply. The curve was elegant, orderly, and stubbornly resistant to classical explanation. This resistance mattered because blackbody radiation was directly connected to thermodynamics, one of the most secure pillars of physics. Heat, temperature, and energy exchange were not exotic concepts, they were central to engines, industry, and everyday experience. If classical physics failed here, it failed at the core of its explanatory power. The blackbody problem therefore threatened not just optics or electromagnetism, but the entire framework linking microscopic motion to macroscopic heat. The cavity model also carried deep conceptual implications. Inside the cavity, electromagnetic radiation could be treated as standing waves, each with a specific frequency. These waves behaved mathematically like oscillators, systems that classical physics claimed to understand extremely well. The blackbody problem thus became a bridge between electromagnetism and statistical mechanics. It asked whether the same principles that governed vibrating strings and gas molecules could also govern light itself. This is why the failure was so shocking. Every component of the classical description seemed reasonable. Maxwell's equations described electromagnetic waves, statistical mechanics described energy distribution, thermodynamics described equilibrium. Each piece worked beautifully on its own. The blackbody brought them together, and the combination collapsed. The idealized nature of the blackbody left no room to blame impurities, imperfections, or unknown forces. The failure pointed inward, toward the assumptions themselves. The importance of the blackbody also lies in its role as a universal benchmark. Even today, blackbody radiation serves as a reference point in physics and astronomy. The cosmic microwave background radiation, for example, follows an almost perfect blackbody spectrum, revealing information about the early universe. This modern relevance underscores how foundational the concept truly is. The blackbody is not a historical artifact, it is a lens through which nature reveals its most basic patterns. In the late 19th century, however, this universality was precisely what made the problem unbearable. If the blackbody spectrum was universal, then any correct theory of radiation had to reproduce it exactly. Approximate agreement was not enough. Partial success at some wavelengths could not compensate for total failure at others. The blackbody demanded a complete explanation, and classical physics could not provide one. The deeper reason the blackbody mattered is that it exposed the relationship between matter and radiation as something fundamentally new. Radiation was not just an accessory to matter, nor was it merely a wave propagating through space. In the blackbody cavity, radiation reached equilibrium with matter, exchanging energy continuously. This intimate coupling suggested that understanding radiation required understanding matter at a deeper level than classical physics allowed. Thus, the blackbody was not merely a technical construct, but a philosophical challenge. It asked whether the laws derived from everyday experience could truly govern the microscopic exchange of energy. It forced physicists to confront the possibility that continuity, one of their most cherished assumptions, might not apply universally. By insisting on universality and simplicity, the blackbody stripped physics of its comforting complexity and revealed a gap at its core. In this sense, the blackbody mattered because it was unforgiving. It did not allow theories to hide behind complexity or approximation. It demanded exactness, and in doing so, it exposed the limits of classical thinking. The glow of a heated cavity became a mirror reflecting the inadequacy of existing ideas. From that reflection would emerge a radically new understanding of nature, but only after physicists fully grasped what the blackbody truly was and why it refused to be explained away. As physicists dug deeper into the meaning of the blackbody, its importance only grew more unsettling. What initially looked like a clever experimental trick gradually revealed itself as a fundamental probe into the nature of reality. The blackbody was not just a convenient approximation. It was a system in which matter and radiation reached a perfect balance. In that balance, every classical assumption about energy exchange was put under maximum stress. Nothing could be hidden, averaged out, or ignored. One of the most revealing aspects of the blackbody was that it erased memory. Radiation inside a cavity lost all information about how it entered or what material the walls were made of. After enough reflections, the radiation depended only on temperature. This loss of memory was deeply significant. It suggested that blackbody radiation represented a kind of thermal equilibrium more fundamental than any specific material process. The system behaved as if it were obeying a universal law written into nature itself. This universality turned blackbody radiation into a standard of truth. If a theory claimed to describe thermal radiation, it had to reproduce the blackbody spectrum exactly. There was no room for adjustment based on chemical composition, surface roughness, or experimental setup. The blackbody function was the same everywhere, for everyone, every time. This made it an unforgiving test of theoretical ideas. Partial explanations were meaningless if they failed even slightly. As experimental precision improved, patterns within the blackbody spectrum became clearer. One of the most striking was the systematic shift of the peak wavelength with temperature. As objects became hotter, the wavelength at which emission was strongest moved steadily toward shorter values. This behavior was captured empirically by Wilhelm Wien, whose work demonstrated that temperature and wavelength were linked by a simple inverse relationship. This law worked beautifully, but only described part of the spectrum. It was a clue, not a solution. The existence of such empirical laws made the theoretical failure even more frustrating. Nature was clearly following precise rules. The curve was not chaotic or irregular, it was smooth, elegant, and mathematically structured. The problem was not that radiation was mysterious, but that the wrong concepts were being used to describe it. Classical physics could see the pattern, but could not explain its origin. The cavity model also forced physicists to confront the role of boundaries and confinement. Inside the cavity, radiation did not behave like free waves traveling endlessly through space. It formed standing waves, constrained by the geometry of the walls. Each allowed mode had a specific frequency. This discreteness of modes came from boundary conditions, not from any assumption about energy itself. Classical theory treated these modes as continuously variable in energy, even though their frequencies were discrete. This subtle distinction would later prove crucial. At the time, however, this distinction went largely unnoticed. Physicists were comfortable with the idea that systems could have discrete configurations while still exchanging energy continuously. Vibrating strings, for example, have discrete modes but continuous amplitudes. The blackbody cavity was treated in the same way. No one initially suspected that the real problem lay not in the modes, but in the energy they carried. The importance of the blackbody also extended beyond laboratories and theory rooms. Industrial advances depended on understanding heat, light, and radiation. Furnaces, lamps, and engines all operated in regimes where thermal radiation mattered. An inability to explain blackbody radiation was not merely an academic embarrassment, it signaled a gap in the theoretical foundations underlying modern technology. Physics could describe how machines worked, but not why heated matter radiated energy the way it did. This gap exposed a deeper issue in the relationship between theory and experiment. Classical physics had grown increasingly abstract and mathematical, yet it had always maintained a strong connection to measurable quantities. The Blackbody problem showed that mathematical elegance alone was not enough. The equations could be beautiful, internally consistent, and still fundamentally wrong. Nature did not negotiate with theory. As the significance of the Blackbody became clearer, it began to change how physicists thought about idealization itself. Idealized systems were supposed to simplify reality in a way that preserved essential behavior. In this case, idealization had done the opposite. By removing material complications, it revealed a contradiction that real-world complexity had previously masked. The Blackbody was not hiding reality, it was exposing it. This exposure also challenged the reductionist mindset of classical physics. The prevailing belief was that macroscopic behavior could always be reduced to microscopic motion governed by known laws. The Blackbody problem suggested that this reduction might fail if the microscopic laws themselves were incomplete. Radiation, though describable by waves, did not fit neatly into the same statistical framework as particles. The Blackbody stood at the intersection of these domains, and classical physics could not reconcile them. Over time, the Blackbody came to be seen as a boundary object, marking the edge of classical understanding. On one side lay the familiar territory of continuous variables and deterministic laws. On the other lay an unknown landscape where energy exchange followed unfamiliar rules. The Blackbody did not reveal what those rules were, but it made their existence unavoidable. This is why the Blackbody mattered so deeply. It was not just another phenomenon to be cataloged. It was a diagnostic tool that tested the health of an entire theoretical framework. When the framework failed, the failure was unmistakable and irreparable within existing assumptions. The Blackbody did not allow physics to remain comfortable. The importance of this realization cannot be overstated. Without the conceptual clarity provided by the Blackbody, the crisis in radiation theory might have been postponed or misunderstood. Complex materials and messy systems could have obscured the deeper issue for decades. The simplicity of the Blackbody forced physics to confront the problem head-on. In retrospect, the Blackbody can be seen as a teacher rather than an obstacle. It taught physicists where classical ideas stopped working. It demonstrated that universality, not complexity, is often the most powerful revealer of truth. By demanding an explanation that applied everywhere and always, the Blackbody exposed the limits of 19th-century thinking. The refusal of Blackbody radiation to yield to classical explanation was not a failure of experimentation or imagination. It was a signal that nature was structured in a way that classical physics could not capture. The Blackbody mattered because it made that signal impossible to ignore. It stood quietly in laboratories, glowing with heat, while undermining centuries of assumptions. Ultimately, the Blackbody's importance lies in what it forced physics to become. It compelled the abandonment of unquestioned continuity. It demanded new concepts to describe energy exchange. It transformed idealization from a simplifying assumption into a revolutionary tool. And most importantly, it showed that even the most ordinary phenomena can carry within them the seeds of profound change. The Blackbody was not dramatic or exotic. It did not require extreme conditions or cosmic scales. It required only careful observation and intellectual honesty. In its silent, steady glow, it revealed that the universe was deeper, stranger, and more structured than classical physics had ever imagined. From that realization, a new era of physics was born. The ultraviolet catastrophe was not a dramatic event announced with alarms or sudden discoveries. It emerged quietly from equations that physicists trusted, calculations performed with confidence, and assumptions that had never seriously been questioned. Yet its implications were so extreme that once understood, they shook the foundations of physics. The catastrophe lay not in experiments exploding or theories collapsing overnight, but in the calm, logical prediction that ordinary objects should emit infinite energy. This prediction was so absurd that it exposed a deep and unavoidable flaw in classical thinking. To understand why the ultraviolet catastrophe was so disturbing, one must return to the classical picture of radiation inside a cavity. According to electromagnetic theory, radiation could be represented as standing waves trapped between the walls. Each standing wave corresponded to a specific frequency, determined by the geometry of the cavity. These waves were mathematically similar to harmonic oscillators, systems that classical physics believed it understood thoroughly. There was nothing mysterious about them. They were predictable, continuous, and well-behaved. Statistical mechanics then entered the picture. This framework was designed to connect microscopic motion with macroscopic properties like temperature and pressure. One of its central results was the equipartition theorem, which stated that in thermal equilibrium, each independent degree of freedom contributes an equal amount of energy. Applied to the electromagnetic field, this meant that every standing wave mode should carry the same average energy, proportional to temperature. This assumption had worked beautifully for gases and solids, reinforcing confidence in its universality. The problem arose when physicists counted how many modes existed. At low frequencies, the number of standing wave modes was modest, but as frequency increased, the number of possible modes increased rapidly. In fact, there was no upper limit. Classical theory allowed arbitrarily high frequency waves to exist inside the cavity. When equal energy was assigned to each of these infinitely many modes, the total energy diverged. Mathematically, the integral describing the energy density blew up at short wavelengths. Physically, this meant infinite energy emission in the ultraviolet region and beyond. This was not a minor discrepancy. It was a complete breakdown. The theory did not merely overestimate the energy slightly, it predicted an impossible outcome. Infinite energy could not be produced by a finite system at a finite temperature. The laws of thermodynamics alone made this prediction unacceptable. Yet the mathematics followed directly from principles that had never failed elsewhere. This contradiction created a crisis that could not be ignored. The ultraviolet catastrophe earned its name precisely because of this explosive divergence. The term, ultraviolet, referred to the short wavelength end of the spectrum where the predicted energy density skyrocketed. The term, catastrophe, reflected the total failure of classical theory in this regime. It was as if the equations lost all contact with reality exactly where they should have remained most reliable. What made the catastrophe particularly painful was that classical theory worked extremely well at long wavelengths. The Rayleigh-Jeans law, derived from classical assumptions, matched experimental data almost perfectly in the infrared and microwave regions. This partial success reinforced the belief that the overall framework was correct, but the same law led inexorably to infinite energy at high frequencies. The theory was both right and disastrously wrong at the same time. This duality deepened the confusion. If the assumptions were fundamentally flawed, why did they work so well in part of the spectrum? If they were valid approximations, why did they fail so completely elsewhere? The ultraviolet catastrophe thus raised a subtle but profound question. Could a theory be approximately correct in one regime and utterly wrong in another? Classical physics had rarely confronted such a stark boundary. Experimental evidence left no room for doubt. Measurements showed that the intensity of blackbody radiation rose to a peak and then declined rapidly at higher frequencies. There was no hint of divergence, no trace of infinite energy. The discrepancy between theory and experiment grew worse as measurement precision improved. The catastrophe was not an artifact of poor data, it was a theoretical fiction imposed by incorrect assumptions. The implications went beyond radiation theory. The ultraviolet catastrophe challenged the continuity of energy itself. Classical physics assumed that energy could be divided indefinitely, exchanged in arbitrarily small amounts, and distributed smoothly across all possible modes. The catastrophe suggested that this assumption might not hold at small scales. If energy could not actually populate infinitely many modes, then something must be restricting its distribution. At first, physicists hoped that matter itself might provide this restriction. Perhaps atoms could not respond to very high-frequency radiation, or perhaps interactions between matter and radiation suppressed short wavelength modes. These ideas were explored, but they failed to resolve the problem consistently. The catastrophe arose even when radiation was treated independently of specific material properties. The issue was deeper than atomic structure as it was then understood. The crisis revealed a limitation in the classical picture of oscillators. Harmonic oscillators were assumed to be able to absorb and emit energy continuously at any frequency. But what if this assumption was wrong? What if oscillators behaved differently at high frequencies? The ultraviolet catastrophe hinted that the classical model of oscillators might be an approximation that broke down under certain conditions. The psychological impact on the scientific community was significant. Physics had enjoyed a long period of success, and the idea that its core principles might be incomplete was unsettling. Many physicists regarded the ultraviolet catastrophe as an embarrassing anomaly rather than a sign of deeper trouble. There was a strong desire to fix the equations without abandoning the underlying worldview. This resistance delayed acceptance of more radical ideas. Yet the catastrophe could not be patched away. It was not a small correction problem, it was a fundamental inconsistency. Infinite predictions in physics are often interpreted as signals that a theory has been pushed beyond its domain of validity. In this case, the signal was loud and unmistakable. The ultraviolet catastrophe declared that classical physics could not be the final word on nature. In hindsight, the catastrophe can be seen as a boundary marker. It identified the edge beyond which classical concepts cease to apply. Just as Newtonian mechanics fails at relativistic speeds, classical radiation theory failed at high frequencies. The difference was that this failure appeared in everyday thermal phenomena, not extreme astrophysical conditions. This made it impossible to ignore. The ultraviolet catastrophe also reshaped how physicists thought about explanation itself. A correct theory had to do more than fit data, it had to avoid absurd consequences. Infinite energy was not merely incorrect, it was meaningless. The catastrophe forced physicists to confront the possibility that their mathematical tools, though powerful, were being applied under false assumptions. This realization prepared the ground for a conceptual leap. If classical ideas led inevitably to catastrophe, then avoiding catastrophe required abandoning at least one classical assumption. The challenge was to identify which assumption to sacrifice. Continuity of energy, universality of equipartition, and classical oscillator behavior all came under suspicion. The stage was set for a radical rethinking of energy exchange. Thus, the ultraviolet catastrophe was not just a problem to be solved, it was a revelation. It exposed the limits of classical physics with brutal clarity. It showed that nature does not permit infinite energy densities, and that any theory predicting them must be incomplete. In doing so, it transformed a technical failure into a philosophical turning point. The catastrophe's true significance lies in what it made unavoidable. It forced physicists to accept that something fundamentally new was required. The smooth, continuous world of classical physics could not fully describe the microscopic realm. The glow of heated objects, so familiar and mundane, had revealed a crack in the foundations of science. From that crack would soon emerge an entirely new way of understanding reality. As physicists grappled with the ultraviolet catastrophe, its deeper meaning slowly came into focus. What initially seemed like a mathematical embarrassment began to look like a profound warning. The catastrophe was not an isolated flaw in one corner of physics, it was a symptom of a deeper incompatibility between classical ideas and the way nature actually distributes energy. The more carefully the problem was examined, the clearer it became that no amount of technical refinement could save the classical framework intact. One of the most unsettling realizations was that the catastrophe arose precisely because classical theory was being applied correctly. There was no mistake in the mathematics, no hidden algebraic error waiting to be discovered. Each step followed logically from accepted principles. This meant that the problem could not be solved by better calculations or more sophisticated techniques. The assumptions themselves were leading physics to an impossible conclusion. That realization marked a psychological turning point. because it forced physicists to confront the limits of reasoning that had guided them for generations. The catastrophe also exposed a subtle but critical mismatch between theory and physical meaning. In classical physics, mathematical variables were often assumed to correspond directly to physical reality. If an equation allowed a quantity to vary continuously without bound, it was assumed that nature permitted the same. The ultraviolet catastrophe shattered this assumption. The mathematics allowed infinite energy at high frequencies, but nature did not. This disconnect raised a disturbing question: could it be that mathematics, when guided by the wrong physical assumptions, leads reliably to nonsense? As this question spread through the scientific community, it began to erode confidence in one of the most cherished principles of 19th century physics: universality. Classical laws were believed to apply equally well at all scales. The ultraviolet catastrophe demonstrated that this belief was untenable. The same principles that worked at low frequencies failed completely at high ones. Physics was being forced to accept that its laws might be scale-dependent, valid only within certain domains. The catastrophe also highlighted the danger of relying too heavily on analogy. The electromagnetic field had been treated as a collection of oscillators because oscillators were well understood. This analogy worked mathematically, but the catastrophe suggested that it might be physically misleading. Radiation was not simply a mechanical system in disguise. Treating it as such had produced results that defied physical reality. The breakdown of this analogy hinted that radiation possessed properties that classical mechanics could not capture. Another crucial implication was the challenge posed to determinism. Classical physics assumed that if the state of a system were known exactly, its future behavior could be predicted with certainty. The ultraviolet catastrophe undermined this confidence indirectly. If classical laws led to infinite energy densities, then either nature behaved in an unphysical way or the laws themselves were incomplete. In either case, determinism could no longer be taken for granted as a universal principle. The catastrophe also forced physicists to rethink the meaning of equilibrium. Thermal equilibrium was supposed to represent a state of maximum stability and balance. Yet classical theory predicted that equilibrium radiation contained infinite energy. This contradiction struck at the heart of thermodynamics. If equilibrium itself was being misdescribed, then the connection between microscopic motion and macroscopic heat was fundamentally flawed. The catastrophe thus called into question the very idea of how systems settle into stable states. As debates intensified, it became clear that the ultraviolet catastrophe was not something that could be postponed or ignored. Every attempt to push it aside only made it return more forcefully. The problem appeared in textbooks, lectures, and research papers, quietly undermining confidence in the completeness of physics. Younger physicists, in particular, began to sense that they were witnessing the end of an era. The classical worldview, so coherent and powerful, was showing signs of irreversible strain. The catastrophe also served as a lesson in scientific humility. For decades, physics had advanced by extending existing principles into new domains. This strategy had worked so well that it became almost automatic. The ultraviolet catastrophe demonstrated that extension without re-examination can be dangerous. When principles are applied beyond their natural limits, they may produce results that are not just inaccurate, but meaningless. In time, the catastrophe came to be understood as a boundary marker rather than a failure. It showed precisely where classical physics stopped being reliable. This realization was invaluable. Knowing the limits of a theory is as important as knowing its successes. The ultraviolet catastrophe mapped the frontier between the classical and the unknown, making it possible to search deliberately for new principles rather than stumbling blindly. Perhaps the most important consequence of the catastrophe was that it reframed failure as opportunity. The impossibility of infinite energy forced physicists to imagine alternatives that had previously seemed unnecessary or even absurd. If energy could not be distributed continuously across infinitely many modes, then some restriction had to exist. The nature of that restriction was still unknown, but the need for it was undeniable. The catastrophe demanded innovation. This demand reshaped the culture of physics. It encouraged a willingness to abandon deeply held assumptions when evidence required it. It taught that elegance and tradition must yield to reality. The ultraviolet catastrophe did not provide answers, but it made certain questions unavoidable. What is energy really? How is it exchanged? Are continuity and determinism fundamental, or merely approximations? By forcing these questions into the open, the catastrophe transformed a technical inconsistency into a philosophical turning point. It revealed that the classical picture of the universe, though powerful, was not complete. The infinite predictions at high frequencies were not just wrong numbers, they were signals that the underlying concepts were inadequate. In this sense, the ultraviolet catastrophe was a creative destruction. It dismantled the illusion that physics was finished and cleared space for a new framework to emerge. It showed that nature was not obligated to conform to human expectations of smoothness and continuity. The glow of heated matter, analyzed with honesty and precision, had exposed the limits of an entire worldview. The true legacy of the ultraviolet catastrophe lies in this exposure. By pushing classical physics to its breaking point, it revealed where new ideas were needed most urgently. It taught physicists that progress sometimes begins with impossibility. From the recognition that infinite energy could not be real, a radically different understanding of energy would soon arise. The catastrophe was not the end of physics, but the moment it was forced to grow up and face a deeper reality. At the height of the Blackbody crisis, when classical physics seemed trapped between mathematical rigor and physical absurdity, a quiet and methodical figure stepped forward with an idea that would permanently alter the course of science. Max Planck was not a revolutionary by temperament. He was deeply committed to order, continuity, and the traditional values of 19th-century physics. Yet it was precisely his respect for rigor that led him to make one of the most radical moves in scientific history. Planck approached the Blackbody problem not as a philosophical rebellion, but as a practical challenge. The experimental curve of Blackbody radiation was undeniable, and the failure of classical theory to reproduce it was complete. Rather than attempting to rescue existing assumptions, Planck focused on finding a mathematical expression that fit the data exactly. His motivation was not to overthrow classical physics, but to preserve it by any means necessary. Ironically, this conservative intent produced a revolutionary outcome. In studying how energy was exchanged between matter and radiation, Planck modeled the walls of the blackbody cavity as containing microscopic oscillators. These oscillators absorbed and emitted electromagnetic radiation. Classical theory assumed that such oscillators could exchange energy continuously in arbitrarily small amounts. Planck made a single, extraordinary departure from this assumption. He proposed that the energy of these oscillators could only take on discrete values proportional to their frequency. Energy, he suggested, was not exchanged smoothly, but in finite packets. This assumption was not derived from experiment in the usual sense, nor from deeper theoretical principles. Planck introduced it as a formal hypothesis, a mathematical constraint imposed on the system. He later described this step as an act of desperation. Yet when he applied this idea to the blackbody problem, the result was astonishing. The new formula matched experimental data perfectly across the entire spectrum. The ultraviolet catastrophe vanished instantly, replaced by a finite, well-behaved distribution of energy. What made Planck's move so radical was not the equation itself, but what it implied about nature. By restricting energy to discrete values, he had implicitly denied one of the core assumptions of classical physics: continuity. For centuries, physicists had believed that energy could vary smoothly, like position or velocity. Planck's hypothesis suggested instead that energy behaved more like currency, exchanged in indivisible units rather than poured continuously. At first, Planck did not believe this discreteness reflected physical reality. He regarded it as a mathematical trick, a temporary device that allowed calculations to work while deeper classical explanations remained hidden. He hoped that future developments would explain why quantization appeared without requiring a fundamental break from classical ideas. In this sense, Planck himself did not fully grasp the magnitude of his own contribution. Nevertheless, the consequences were unavoidable. The constant that appeared in Planck's formula, now known as Planck's constant, set a fundamental scale for nature. It determined the size of the energy packets and established a boundary below which classical concepts ceased to apply. This constant was not a parameter to be adjusted or eliminated. It was fixed by experiment. Nature itself was declaring a limit. Planck's radical move also reframed the relationship between theory and experiment. Classical physics had been built on intuitive principles, later refined by mathematics. Planck reversed this order. He accepted a counterintuitive assumption because it worked, not because it made sense within existing frameworks. This marked a shift in scientific methodology. Empirical success became the guide, even when intuition failed. The deeper irony is that Planck's solution preserved much of classical physics while simultaneously undermining its foundations. At low frequencies and large scales, his formula reduced to classical results, explaining why older theories had worked so well. At high frequencies and small scales, it diverged sharply, preventing infinite energy and restoring agreement with experiment. Classical physics was revealed not as wrong, but as an approximation valid only in certain limits. This duality made Planck's move especially powerful. It did not discard the past, it absorbed it into a broader framework. Yet that broader framework required accepting that energy itself was quantized. Once this idea was introduced, it could not be confined to blackbody radiation alone. It raised new questions about atoms, light, and matter that classical physics could not answer. Although Planck initially resisted these implications, others quickly recognized their significance. The idea that energy comes in discrete units would soon be applied to explain phenomena that had long puzzled physicists. The blackbody problem, once a source of embarrassment, became the gateway to a new understanding of the microscopic world. Planck's radical mathematical move stands as a reminder that scientific revolutions do not always begin with bold declarations. Sometimes they begin with a single assumption, introduced reluctantly, justified pragmatically, and understood only in hindsight. By choosing accuracy over comfort, Planck allowed nature to speak more clearly than theory ever had before. In doing so, he opened the door to quantum physics, not by rejecting classical ideas outright, but by revealing where and why they must give way. The idea that energy is quantized did not arrive as a fully formed theory with clear physical meaning. It emerged gradually, almost reluctantly, from attempts to make sense of experimental facts that refused to fit classical expectations. When the concept first appeared, it was not framed as a revolution in how nature works, but as a mathematical necessity imposed by stubborn data. Yet once introduced, the notion that energy comes in discrete units began to reshape physics at its deepest level, altering how scientists understood light, matter, and reality itself. Energy quantization means that energy is not exchanged continuously, like water flowing smoothly from one container to another. Instead, it is transferred in fixed, indivisible packets. These packets have sizes determined by the frequency of the process involved. This idea stood in direct opposition to classical physics, which assumed that energy could be divided endlessly into smaller and smaller amounts. In the classical view, there was no smallest unit of energy, just as there was no smallest distance or time. Quantization challenged this continuity at its core. At first, quantization appeared only as a property of interaction, not of energy itself. It was introduced to describe how matter exchanges energy with radiation, not to redefine the nature of energy in general. This distinction mattered greatly to early physicists, who were hesitant to abandon classical ideas wholesale. They could accept restrictions on emission and absorption more easily than they could accept discreteness as a fundamental feature of the universe. Quantization was tolerated as a rule of exchange, not yet embraced as a law of nature. The power of the idea became apparent when it resolved the most troubling contradictions of radiation theory. By limiting the ways in which oscillators could store and release energy, quantization prevented the uncontrolled buildup of energy at high frequencies. The infinite predictions of classical physics disappeared. Energy distributions became finite, stable, and consistent with observation. What had seemed like a technical fix began to look like a window into a deeper structure underlying physical processes. This shift had profound implications. If energy could only be absorbed or emitted in discrete amounts, then the microscopic world could not behave like a scaled-down version of the macroscopic one. Smooth motion and continuous change were no longer universal. At small scales, nature appeared to operate in jumps. These jumps were not the result of ignorance or approximation, they were intrinsic. The idea that the universe might be fundamentally granular, at least in certain respects, was both unsettling and exhilarating. The consequences of quantization quickly extended beyond blackbody radiation. In 1905, Albert Einstein applied the idea to explain the photoelectric effect, a phenomenon in which light ejects electrons from a metal surface. Classical wave theory predicted that increasing light intensity should increase electron energy, regardless of frequency. Experiments showed the opposite. Only light above a certain frequency could eject electrons, and the energy of those electrons depended on frequency, not intensity. By treating light itself as quantized, composed of discrete packets of energy, Einstein provided a simple and accurate explanation. This application marked a turning point. Quantization was no longer confined to matter's interaction with radiation, it was now being used to describe light itself. Energy packets, later called photons, became a real physical concept rather than a mathematical convenience. The idea that light could behave both as a wave and as a collection of particles challenged classical categories and forced physicists to rethink the nature of electromagnetic radiation. Quantization also transformed the understanding of atoms. Classical models could not explain why atoms were stable or why they emitted light at specific frequencies. If electrons could orbit a nucleus at any energy, they should radiate continuously and spiral inward, leading to atomic collapse. Quantized energy levels offered a way out. By allowing only specific energies, atoms could be stable, and their emission spectra could be explained as transitions between discrete states. What had once seemed like arbitrary spectral lines became precise fingerprints of atomic structure. The birth of energy quantization thus unified a wide range of phenomena under a single principle. Blackbody radiation, the photoelectric effect, atomic spectra, and later chemical bonding all pointed to the same conclusion: energy at microscopic scales is not continuous. This unity gave the idea enormous explanatory power. It was no longer an isolated hypothesis, but a foundational concept linking diverse areas of physics. Equally important was the philosophical shift that accompanied quantization. Classical physics had been deeply deterministic and continuous. Quantization introduced limits, thresholds, and inherent discreteness. It suggested that not everything could be predicted by smooth equations extending indefinitely. Nature imposed boundaries on what could happen and how it could happen. These boundaries were not imposed by measurement limitations, but by the structure of reality itself. At the same time, quantization preserved continuity where it mattered most. At large scales and low frequencies, quantized behavior blended seamlessly into classical results. Energy levels became so closely spaced that they appeared continuous. This explained why classical physics worked so well in everyday situations. Quantization did not overthrow classical ideas, it explained their success as approximations. This continuity of explanation, despite underlying discreteness, gave the emerging quantum framework both depth and credibility. The gradual acceptance of energy quantization was not smooth or immediate. Many physicists resisted its implications, hoping that a deeper classical explanation would eventually restore continuity. Yet as evidence accumulated, resistance became harder to justify. Each new success reinforced the idea that quantization was not a temporary fix, but a fundamental principle. The birth of energy quantization marked a decisive shift in how physics understood nature. It revealed that the universe is structured in layers, with different rules governing different scales. Smoothness and continuity emerge from deeper discreteness, rather than replacing it. This insight reshaped scientific thinking far beyond physics, influencing ideas about measurement, causality, and the limits of knowledge. What began as an attempt to fix a radiation problem became a new way of seeing the world. Energy quantization showed that nature does not always allow gradual change. Sometimes it demands jumps. By accepting those jumps as real, physics gained access to a deeper and more accurate description of reality, one that continues to shape science and technology to this day. The consequences of the Blackbody problem did not end with its solution. Instead, they spread outward, reshaping physics so thoroughly that the discipline before and after this moment almost seems like two different sciences. What began as a narrow question about thermal radiation became the catalyst for a complete transformation in how physicists understood nature, knowledge, and the limits of explanation. The Blackbody problem did not merely add a new chapter to physics, it forced a rewrite of the entire book. Once energy quantization was introduced and shown to work, it became impossible to confine its implications to blackbody radiation alone. The idea challenged the very foundations of classical physics, which had been built on continuity, determinism, and smooth change. These principles were not minor assumptions, they were the conceptual backbone of centuries of scientific thought. By undermining them, the Blackbody problem triggered a chain reaction that extended into every corner of physics. One of the earliest and most profound shifts occurred in the understanding of atoms. Classical models could not explain why atoms were stable or why they emitted light at specific frequencies. When quantization entered the picture, these mysteries began to dissolve. The atom was no longer a miniature solar system governed by classical orbits, but a system constrained by discrete energy levels. This new view reached a decisive form with the work of Niels Bohr, whose atomic model explicitly incorporated quantized energy states. Although incomplete, it demonstrated that classical mechanics alone could not describe atomic structure. This shift marked a deeper realization. The microscopic world obeys rules that have no direct analog in everyday experience. Concepts like trajectory, position, and velocity, which seemed self-evident at macroscopic scales, lost their clear meaning when applied to electrons and photons. The Blackbody problem had opened the door to this realization by showing that even something as basic as energy does not behave classically at small scales. As quantum ideas developed, they began to reshape the meaning of explanation itself. Classical physics aimed to describe systems in terms of precise causes and effects evolving continuously in time. The emerging quantum framework replaced this picture with probabilities, discrete transitions, and inherent limits on what could be known. This transition reached a new level with the development of quantum mechanics in the 1920s, particularly through the work of Werner Heisenberg and others. The Blackbody problem stands at the beginning of this transformation, the first clear signal that classical determinism was not universal. Another enduring impact was methodological. Before the Blackbody crisis, physics progressed largely by extending existing theories into new domains. The success of this strategy had bred confidence that the fundamental framework was already in place. The failure of classical radiation theory shattered this confidence. It taught physicists that extrapolation has limits, and that even the most successful theories may break down when pushed too far. This lesson profoundly influenced how new theories were evaluated, encouraging greater attention to domains of validity and conceptual assumptions. The Blackbody problem also changed the relationship between mathematics and physical meaning. Classical physics often assumed that mathematically allowed behavior corresponded directly to physical reality. The ultraviolet catastrophe showed that this assumption could be dangerously wrong. Equations could be internally consistent and still describe an impossible world. After this realization, physicists became more cautious, more willing to question whether mathematical formalisms truly reflected nature. This shift helped prepare the ground for abstract quantum mathematics, which demanded careful interpretation rather than intuitive acceptance. Technological consequences followed as well. The quantum understanding of energy and radiation, rooted in the Blackbody problem, eventually made possible semiconductors, lasers, medical imaging, and modern electronics. While these technologies emerged decades later, their conceptual foundations trace directly back to the realization that energy exchange is quantized. The Blackbody problem thus reshaped not only theoretical physics, but the material conditions of modern life. Equally important was the philosophical impact. The classical worldview had presented the universe as a predictable machine, fully knowable in principle. The developments that followed the Blackbody problem replaced this image with a subtler one. Nature appeared structured, lawful, and intelligible, but not fully transparent. There were limits to precision, inherent uncertainties, and behaviors that could only be described statistically. This new worldview challenged long-held assumptions about causality and objectivity. The reshaping of physics was not instantaneous. Classical ideas continued to coexist with quantum ones, and in many domains they remain indispensable. What changed was not the usefulness of classical physics, but its status. It was no longer regarded as the final description of reality, but as an approximation that emerges from deeper laws under certain conditions. This layered understanding of theory became a defining feature of modern physics. The Blackbody problem also influenced how physicists thought about unification. The crisis revealed that phenomena previously treated as separate, such as heat, light, and atomic behavior, were deeply connected. Solving the radiation problem required insights that linked thermodynamics, electromagnetism, and atomic theory. This interconnectedness became a guiding principle in later efforts to unify physical laws. Perhaps the most lasting legacy of the Blackbody problem is the lesson it taught about progress itself. Scientific revolutions do not always begin with bold, new visions. Sometimes they begin with stubborn failures that refuse to go away. The Blackbody problem persisted precisely because it was simple, universal, and experimentally undeniable. Its resistance to classical explanation forced physics to evolve. By reshaping assumptions about energy, continuity, and explanation, the Blackbody problem permanently altered the trajectory of physics. It marked the transition from a world governed entirely by classical intuition to one in which abstraction, probability, and quantization play central roles. The puzzle that once threatened to break physics instead transformed it, revealing a deeper structure beneath familiar phenomena and setting the stage for all of modern quantum science. More than a century after it first unsettled physicists, the Blackbody problem continues to matter, not as a historical curiosity, but as a living example of how science advances and how our understanding of reality deepens. Its importance today lies not only in the equations it inspired, but in the mindset it forced upon physics. The Blackbody problem remains relevant because it illustrates, with exceptional clarity, how fundamental truths are uncovered when simple questions expose hidden assumptions. One of the most enduring reasons the Blackbody problem still matters is that it defines the boundary between classical and quantum descriptions of nature. Modern physics relies on a layered understanding of reality, where classical laws emerge as approximations of deeper quantum principles. The Blackbody problem was the first clear demonstration of this structure. It showed that classical ideas are not wrong, but limited. This lesson remains central in contemporary research, where scientists constantly test whether existing theories apply at new scales or energies. The Blackbody spectrum itself continues to play a crucial role in modern science. In astronomy and cosmology, Blackbody radiation serves as a benchmark for understanding the universe. The most famous example is the cosmic microwave background, a nearly perfect Blackbody signal left over from the early universe. Its precise shape encodes information about the age, composition, and evolution of the cosmos. Without the theoretical understanding born from the Blackbody problem, This signal would be unintelligible noise rather than a window into cosmic history. The problem also matters because it established the concept of fundamental constants as structural features of reality. Planck's constant, introduced to solve the Blackbody puzzle, is now recognized as one of the basic parameters that define the universe. It sets the scale at which quantum effects become significant. In modern physics, the search for deeper theories often involves asking why such constants have the values they do, and whether they could be different. The Blackbody problem was the moment when one of these constants first revealed itself as unavoidable. In technology, the legacy of the Blackbody problem is woven into everyday life. Devices that rely on quantum principles, from infrared sensors and LEDs to lasers and transistors, operate because energy exchange is quantized. Even thermal imaging, which directly measures radiation emitted by objects, is grounded in Blackbody physics. These applications demonstrate that the Blackbody problem is not confined to textbooks. It underpins practical tools that shape modern society. The problem also remains relevant as a lesson in scientific methodology. It shows the power of idealization when used carefully. The Blackbody was an abstract construct, not a real object, yet it revealed deeper truths than many more complex systems. This approach continues to guide modern physics, where simplified models are used to probe fundamental laws. At the same time, the Blackbody problem warns against blind reliance on established assumptions. Idealization can expose truth, but only if it is accompanied by willingness to question the framework in which it operates. Another reason the Blackbody problem still matters is its philosophical impact. It challenged the belief that nature must conform to human intuition. The transition from continuous to quantized energy required accepting that reality operates in ways that feel unnatural from a macroscopic perspective. This lesson resonates in current debates about the interpretation of quantum mechanics, where questions about measurement, reality, and information remain unresolved. The Blackbody problem reminds us that intuition is a guide, not a guarantee. In contemporary physics, similar crises continue to arise. The incompatibility between quantum mechanics and general relativity, for example, echoes the tension once exposed by the Blackbody problem. In both cases, successful theories fail when applied beyond their domains of validity. The historical response to the Blackbody crisis offers a model for how such challenges might be approached by identifying contradictions, respecting experimental facts, and being open to radical conceptual change. Education is another domain where the Blackbody problem retains its importance. It is often one of the first examples used to show students why quantum theory was necessary. Unlike more abstract quantum phenomena, Blackbody radiation is rooted in familiar experiences of heat and light. This accessibility makes it a powerful teaching tool. It shows that revolutionary ideas can emerge from ordinary observations, encouraging students to see science as a dynamic process rather than a finished body of knowledge. The Blackbody problem also underscores the value of failure in scientific progress. Modern research culture often emphasizes success, prediction, and application. The Blackbody problem reminds us that progress sometimes begins with stubborn failures that refuse to be explained away. Recognizing the significance of such failures requires intellectual courage and patience. This lesson is especially relevant in frontier research, where anomalies may signal the need for new paradigms rather than minor adjustments. Finally, the Blackbody problem matters because it exemplifies how deeply interconnected scientific knowledge is. Solving it required insights from thermodynamics, electromagnetism, statistical mechanics, and atomic theory. This interconnectedness is even more pronounced today, as advances in one field often depend on developments in others. The Blackbody problem stands as an early example of how unification can emerge from crisis. In the end, the Blackbody problem continues to matter because it represents a moment when physics listened carefully to nature and allowed itself to change. It teaches that understanding does not come from forcing reality to fit our expectations, but from adjusting our expectations to fit reality. The glow of a heated object, once a source of confusion, became a guide toward a deeper understanding of the universe. That glow still speaks. It speaks through the background radiation of the cosmos, through the devices we use every day, and through the conceptual framework that underlies modern science. The Blackbody problem reminds us that even the simplest questions can transform our view of the world, and that true progress begins when we are willing to accept that our most trusted ideas may only be part of a larger, richer truth.